Hello students, now we are going to discuss voltage follower circuit. In the operational amplifier, we have studied the applications of two type of circuits. One is open loop circuits and second was closed loop circuits. In the closed loop circuits, we have two types of operational amplifiers. One is inverting amplifier and second is non-inverting amplifier. So now we take the example of non-inverting amplifier. So we are having the inverting terminal grounded and we are applying the input at the non-inverting terminal. So we are having a feedback resistance, that is RF. So this is the diagram for the closed loop non-inverting amplifier. Let the input given is Vi. So in this case, let the difference between the inverting and non-inverting voltage is Vt. So we know that the gain of the operational amplifier for the closed loop circuit is 1 plus Rf over R1. It means that AF is what? The gain of the amplifier, means VO over Vi is 1 plus Rf by R1. Now at this point, suppose we have a condition, if Rf is 0 means short circuit and R1 is infinite means open circuit. So the gain of the amplifier, which is Vi over Vi, that will become 1 plus 0, simply 1. It means that Vo is simply equal to Vi. So in this case, if these two conditions are satisfied, then the output voltage will be exactly equal to the input voltage. It's called as voltage follower circuit. Voltage follower circuit. So when we are applying these two conditions, then the circuit will become like this. We will remove the resistance Rf now because it is short circuit. So we have this one, this is inverting terminal, this is non-inverting terminal. We are applying the input Vi at this point and further it is grounded. Now this R1 is infinite, means we have not connected this inverting terminal to any input supply. So we have this kind of circuit diagram. So this operational amplifier is called as voltage follower. Basic function of this comparator is to compare the two values of the input voltage applied at the inverting and the non-inverting input. Now we are having operational amplifier with its two inputs, that is inverting terminal and that is non-inverting terminal. Let V1 is the value of voltage which is applied at the non-inverting terminal and V2 is the voltage which is applied at the inverting terminal. Let Vd is the potential difference between these two terminals and Vo is your output voltage. So we have two more terminals. These are called as the reference terminals. One is plus VCC and second is minus VCC. So in this case, if V1 is greater than V2, then Vo is equal to VOH, and if V1 is less than V2, then Vo is equal to VOL. Vo is equal to VO. high positive voltage and VOL is low negative voltage. So in this case, if we want to draw its characteristic, which is called as voltage transfer characteristic, also known as ideal comparator, its voltage transfer characteristic is shown in the diagram. If VD is greater than 0, therefore your VO is equal to VOH, and if VD is less than 0, then it is equal to VOL, where VD is, what is VD? VD is the difference of potential between non-inverting voltage and inverting. So its graph looks like as a, this is our output voltage and this is our difference potential. If VD is greater than 0, means we are working for the positive x-axis. So your output is VOH, this is VOH, and if VD is less than 0 for this side, then the voltage is VOL. So this is the ideal characteristic for the signal VR, and this is signal VI. This is at the inverting terminal and VI is at the non. VR is a DC voltage and VI is a sinusoidal signal, which is given by VI is equal to V0 sine of omega t. So in this case we are having, this is our VI signal and this is our V reference signal. This is our portion. From this point to this point, your VR signal is more in comparison to VI. Means that VD, which is the difference of VI minus VR, from this point to this point, your VD is negative. It means that our output voltage is negative. So we have two levels here. This is VOH and this is VOL. From this point to this point, your VI is less than VR. It means that your output voltage will be equal to VOL. And from this point to this point, from here to this point, the value of VI is greater than VR. So we will get the output positive voltage. Clear? So now from this point to this point, from this point to this, suppose I am writing this is point P and this is point Q. From this point P to the point Q, the value of VI is less than VR. It means that our output will be VOL. And from PQ to, let's point is S. Now from point Q to S, the value of VI is again greater than VR. So the output will be, we can compare these two signals, VI and VR, and we will get a result which is a square wave. So in this case we can compare two types of signals.